Okay, so we are now starting the exercises of this section, and this is the first one, exercise 841. Here we have to prove that proposition 847 is a consequence of the axiom of choice. That is the first thing. And also conversely, if we assume proposition 847 to be true, then the axiom of choice is a consequence of that. And for the first part, hint is also given. So regarding this hint, let's go back to the statement of 847 briefly. So in 847, the thing is just this: we are given two sets x and y such that for each element x in x and each element y in y, there is a statement p of x comma y that depends on x and y, of course, these elements, such that there is a condition that p satisfies, namely that for each element x in x, there is at least one element y in y for which this statement is true. Then proposition 847 asserts that there is a function from x into y such that p of x comma f of x is going to be in y, okay, is true for all x in x. So this is what we have to prove, assuming that the axiom of choice is there, it is true. And for that we have to, there is a hint and we are going to follow this hint. For each element x in x, we will consider the set yx consisting of those elements of y for which this p of x comma y is true. So let's start the solution accordingly and see where we go. First, we assume the axiom of choice. Okay, and now we have to prove the existence of this function f, and this hypothesis also we are now going to assume, because once these are given, then only this proposition is asserting that such a function exists. So let x comma y be sets such that these conditions are true. If you want, you can just simply take this view that since we are talking about proposition 847, so the hypotheses are already there, but it does not harm to write these things again. Okay, let this be sets such that for each element x in x and y in y, there is a statement px comma y such that, it's a somewhat long sentence, but let's see. For each x in x, there exists at least one y in y for which the statement p is true. is true. Okay, so now we define those sets y suffix x for each x in x. Define yx to be the set of those elements y in y for which this is true. Okay. So now, what does our hypothesis say about these sets? Namely, that each such set is non-empty, obviously, because that's what our hypothesis is. The condition that P satisfies is that for each x in x, there is at least one y for which P of x comma y is true, and yx is the set of such y's for which P of x comma y is true. Because there is at least one y for which this is true, so there is at least one element in this set x, in this set yx. Thus, or then, for each x in x, yx is a non-empty set. So that means we are looking at a family of sets. Which sets? Yx. And the index set in this case is x, because the elements in x are labeling these sets. That's how this thing is, and such that each set in this family is non-empty. So this is a perfect place to apply the axiom of choice. Then, or thus, by the axiom of choice. What does the axiom of choice say? It says that in such a situation, the Cartesian product of all these sets yx is going to be non-empty. So that is our conclusion from the axiom of choice. The product of all these sets yx is non-empty. So that means there is at least one element, and we know how what type of elements there are in such a product. These are tuples. What type of tuples? X tuples. So you choose an element, say yx, this, an x tuple in this Cartesian product. Okay, now if you go back to the definition of what this object is, definition based on functions, then actually an x tuple is itself a function. What type of function? It's a function from x into what? Into the union of all these sets yx. But it's not just an arbitrary function of this type, but it has a condition on it. The condition is that yx is coming from the set yx for each x belonging to x. In fact, that's what the definition of an X tuple is. So let's write these things. Then the X, let's just write the word X tuple, okay. Is a function from X into the union. Actually, there is no need to mention that it's a function from X into this set, but why not? Why keep things incomplete? Such that condition is in fact the main thing that we want to write, we want to mention here. Such that yx belongs to yx for each, okay. It would have been nice if I gave this function a name. Let me, okay. Instead of writing these things in words, let me use the mathematical notation itself for function. That way it will look better. I mean, we will see what I'm trying to say here. It's a function f from X into the union of all the sets yx, such that this yx belongs to yx for each x belonging to x. Thus, now we can change this range slightly. You know that these yx's are all subsets of y by definition. So their union is after all a subset of y. Now if in this function you replace this range with y, then essentially nothing changes. Okay. Actually we get another function, but the rule remains the same and these properties remain the same. Only the range changes. But just for the sake of what we are trying to prove, I am now going to change the range. Thus, we have a function f from x into y such that okay. Something else also should have been written, no? Then when I wrote this in words without giving the function any name, this was enough. But now we have to say such that f of x is equal to yx and yx belongs to this, okay, such that, let's repeat this part, f of x is equal to yx for each x in x, that's understood. Okay, but let's now recall what yx was originally. Yx is the set of those y in y such that p of x comma y is true. Okay, and now the fact that for each x in x, yx belongs to yx means what in terms of this p? It just means that p of x comma yx is true. each x in x, and in place of this yx you can actually write f of x. So let's write in steps, okay, without skipping anything. So, or in other words, this is true for each x in x, or P of x comma f of x is true for each x in x, and this is precisely the conclusion of theorem 84, proposition 847 that we wanted to prove. So one half of our solution is over. Now we are going to look for the converse. Conversely, assume that that theorem, why do I keep calling it theorem? It's proposition. Proposition 847 is true. Let's assume that, and then we have to prove that the statement of axiom of choice is true. Assume that proposition 847 is true. Okay, so that means all existence of such a function satisfying these properties, those things are there, and now we have to prove the axiom of choice. So that means we have to first of all gather the ingredients for the axiom of choice. Let's see the hypothesis. Let I be a set, and let for each element alpha in I there exists a bug has entered. Anyway, let's just concentrate on this. There exists a non-empty set x alpha. Okay, now what is it that we have to prove? We have to prove that this Cartesian product is non-empty, because that's the axiom of choice. So the thing here we have to apply is, of course, this proposition 847, but in order to apply this proposition, you need that P, that statement P. So where will that come from? That is the question. And the thing that you have to do here is this. So you see, P of course will come only after you have the sets x and y, because from them only the elements x and y are going to come respectively. So what are our sets x and y in this case? They are these. For, I think I need ink, just give me a moment. The x in this case, we are going to take I as x, and for y we are going to take the union of these sets x alpha. For it's not coming though. For each alpha in I, for each alpha in I hope it's visible, it will come, and each x in A. Okay, instead of calling it A, let me call it Y itself, or let me call it Y prime. Where what is Y prime? Y prime is the union of all the sets X alpha, as alpha varies over I, of course. So this is our first set in place of that X, which is I, and this is our second set Y prime. So previously we took X from X and Y from Y. Now we are taking alpha from I and X from Y prime. We defined the statement P of alpha comma X to be this statement. This statement that X belongs to X alpha. Okay. Does it make sense? It makes sense because here I, of course, is a set, and the union of these sets X alpha is, of course, again a set by the axiom of union. For each element alpha from I and each element X from Y prime, we have created a statement P of alpha comma X, and the statement is this: X belongs to X alpha. For a given alpha and given X coming from these sets, it may be true, it may be false, but it's after all a statement, a legitimate statement. Now the thing that we have to verify for P is whether we have at least one X for each alpha such that this statement is true, because then we will be able to apply proposition 847. And this is where non-emptiness of the X alphas will play a role. Since X alpha is non-empty for each alpha, so it is that place where do you remember we encountered one result called single choice. It is actually something very obvious, but it was nevertheless proved at some point when we were studying set theory in detail in the third chapter. This result says that if you have a non-empty set X, then you can choose some element from X. That's just it. That is the content of this result, single choice. And the item number was, do I have it here? Yeah, lemma 316. Allows us to choose some X in X alpha for each alpha in I. But then for this alpha and this X, by definition P of alpha comma X is true, naturally. So for each alpha in I, there is at least one x in x alpha, of course, but because y prime is the union of all such x alphas, so this x that we are going to choose from here after all is in y prime. Okay, for which p of alpha comma x is true. So yes, now we are in a position to be able to apply this proposition 847. Hence, by proposition 847, there exists a function f, okay, from the first set to the second set. That means from I into y prime. Let's just write what y prime is. That way it will be easier to interpret things later on. But this has that property, right? Such that p of alpha comma f of alpha is true for each alpha belonging to I. Now let's see what this thing being true means. It means that this second coordinate belongs to x alpha for each alpha. Hence, this belongs to for each alpha belonging to I. But now you look at this. You see, what type of function is f? F is a function from I, the index set, into the union of those sets which I is indexing, such that f of alpha belongs to x alpha for each alpha belonging to I. Hence, or this implies what? This just simply implies that f is nothing but an I tuple, and that too not just any I tuple, an I tuple that actually belongs to the Cartesian product of the sets x alpha. So this implies that f, let me just directly write it instead of writing f is an I tuple, because if I just simply write this, then that automatically means x is an I tuple. Hence, so that's it. We have been able to show that there is at least one element in this Cartesian product. So the Cartesian product is non-empty, and that is the conclusion of the axiom of choice. Hence, this is non-empty. Thus, the axiom of choice is true. And that's how we have come to know that the statement or the entire thing, which is proposition 847, is actually equivalent to the axiom of choice. If you assume any one of it, then the other is a consequence of that, like this. Proposition 847 is equivalent to the axiom of choice. And as the author mentioned, there are other statements which are also equivalent to the axiom of choice. A consequence of this is that in our Zermelo-Fraenkel choice set theory, in all those axioms, if you replace this choice axiom with any of these equivalent statements, then nothing actually logically changes. So we have the same logical system. So let me just end the video here itself. There are two more exercises in this section which we are going to see in the next analysis update. And there is one more section in this chapter which treats order relation and its generalization, which actually I am going to skip. I will leave the entire section to you. It's not as important. There are some things like Zorn's lemma, those things are there, but I leave the entire section to you. You see what you can do with the section. If you do not understand something, please write in the comment section below. And so that means once this section is over, we are going to move over to the next chapter, and which is continuous functions on the system of real numbers, which is where properly our calculus or analysis will begin. So we will do that, and our next upload is this coming Tuesday, of course, and on Tuesday let's go back to number theory. So that's just it for tonight. So see you on Tuesday with number theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.